Chapter 4: Positional Encoding. We have vectors for our words, but so far the model has no idea what order they came in. And order changes everything. Let's fix that. Order carries meaning. The dog bit the man. Now swap two words, the man bit the dog. Same words, completely different story. A language model absolutely must know position. But here is the catch: the attention step we are about to build treats its input as an unordered set. It sees a bag of word vectors with no built-in sense of first or second or last. Let's see the problem directly. Take the cat sat in the scrambled version sat cat the. The embeddings are exactly the same three vectors, just handed over in a different arrangement. To a system that ignores order, these two inputs look identical. So we need to stamp each vector with where it sits in the sentence. Here is the elegant fix. We create one more vector for every position. A vector that means position 0, another that means position 1, position 2, and so on. Then we simply add the position vector to the word vector. Final input equals token embedding plus position embedding. Same size, just added together, element by element. Why does adding work? Watch the word the. It appears twice in our sentence, at position 0 and at position 4. Same word, same embedding. But now we add a different position vector to each one. The two copies land at different points in space. The model can finally tell them apart, meaning plus location in a single vector. So what do these position vectors actually look like? In the original transformer, they are built from sine and cosine waves. Each dimension of the vector is a wave of a different frequency. The formula, position encoding at position p, uses sine of p, divided by 10,000 raised to a power that grows with the dimension. Low dimensions wiggle fast, high dimensions wiggle slowly. Stack those waves up, and every position gets a unique fingerprint. Read down the column at position 3 and you get one specific pattern of values. Position 4 gives a slightly different one. And here is the clever part: nearby positions have similar fingerprints. So the model can feel not just where a word is, but how far apart two words are. One quick note for the curious. Those fixed sine waves were the original recipe. Many modern models instead learn their position vectors from scratch, just like word embeddings. And the newest ones use a trick called rotary embeddings, which rotates each vector by an angle set by its position. Different math, same goal: tell the model where each token sits. So, positional encoding. Attention alone is order blind, so we add a position vector to every token embedding. Now each vector carries both meaning and place. That combined vector is finally ready for the heart of the transformer. Next, the big one, attention.